Well, good morning and welcome to the last physics class of the 2019-2020 school year. And we're going to finish off chapter 28. We're going to finish what we're going to do in modern physics and quantum physics. And you've got a summary to do tomorrow. It's an open book, open note summary. So here we go. We talked yesterday about the de Broglie equation and how we find wavelengths for particles. And an equation for doing that is the Schrodinger wave equation. And this is the equation that is done for one-dimensional components. And I believe this is specifically electrons in an atom. And that's the equation. I mentioned h bar to you guys. That's h, Planck constant divided by 2 pi. Those little weird d's are partial differential equations. And the left one has a second order partial differential equation. The right side has a first order partial differential equation. And if I'm not mistaken, that u and that psi in the middle of the psi is actually a function, which is itself fairly complicated. Psi is the answer. That's what you're trying to solve for, is the psi. Oh, that's a dot product. If I'm not mistaken, on the left side, not multiplication, but a dot product, which is a vector product. Anyway, I do think I learned how to do this in school in my modern physics class for like the most simple possible situation, and even then it's pretty nasty math. So we're not going to do that. But see what it does, and I like this diagram. They didn't have this in their PowerPoint. I added it. But see, the key is that because the particle is a wave, the electron has a certain wavelength. Because it has a certain wavelength, the diameter of the circle or the orbit that it is on has to be the right size for it to completely have an integer number of waves. The one on the left is at the right place, so the wavelength comes out to 6 waves. The one on the right, the waves don't meet, and that means the particle can't exist there because the particle is a wave, and because it's a wave, it has to come out even, and so therefore you'd have to either make the circle larger or smaller so that you would end up with either 5 waves or 6 waves. Okay? You don't need to get the details of that, but that's what's going on here with the wave equation, is it actually means it affects the orbits. And this is actually a probability wave. And so we go into what they call orbitals. And if you remember this from phys sci and or chemistry, electron locations were described as orbitals, and it's kind of an electron cloud. You have got these different areas where the electron is most likely to be or least likely to be, and it's all built around these probability waves, the solutions to the Schrodinger wave equation, and you end up with spheres, and then you end up with the lobes and all that stuff. Those are all solutions to the Schrodinger wave equation. And that leads us into, and we're not going to get into it in here because we did in chemistry, the sp, df orbitals and all of that stuff that we did, quantum numbers, that's all built around the Schrodinger wave equation. Okay, Heisenberg uncertainty principle. Oh, sorry. I need to do this on I just missed the number. 1.11. 1.11 is the Schrodinger wave equation. So this is a complex equation that describes the wave of an electron around a nucleus. It's a complex equation that describes the wave of an electron around a nucleus. Okay, so you saw the equation. It's very complex, and it describes how the electron is a wave around the nucleus. Okay, that's what it is. Okay. The Heisenberg uncertainty principle says that if you want to observe an object, at least, it's the result of this statement. It doesn't say this. This is the result of this statement. To observe an object, at least one photon must be reflected or diffracted by it. So if you have an object, a photon is either bouncing off of it or being twisted by it. And because it does that, it actually changes the electron's motion, which means that your very act of observing an object changes the object. Now, it doesn't matter with large objects because photons bouncing off a car don't move the car very much. But a photon bouncing off an electron can have a serious implication. And so as uncertainty in position decreases, the uncertainty in momentum increases. In other words, if you know where an object is, you do not know how fast it's going. If you know how fast it's going, you don't know where it is. Now, the uncertainty, and I actually have done this before, run this equation past my students. I didn't do it this time. But the uncertainty in, say, a car is like a micrometer. And if you're wanting to know where the car is big enough that a micrometer of error doesn't matter to you. Maybe it's a little bigger than that, but something like that. When you're dealing with an electron, the uncertainty can be huge. And so number 12 in 112, the Heisenberg uncertainty principle says that you can either know momentum or you can know position, but not both. You can know position or momentum, but not both. I saw a comic one time. The guy says, well, I can tell you where the Heisenberg conference is or when it is, but not both. Anyway, so that's the uncertainty principle. Wave-particle duality. And this is built around with a concept called complementarity. The concepts of waves and particles are both needed to describe reality. So energy and matter are both waves and particles. And you have to describe them as both waves and particles in order to get all of reality. Now, I'll tell you, this is as mind-bending to a scientist as the Trinity is to a theologian, or the dual nature of Christ is to a theologian. In all seriousness, it's a very similar concept because it says that either it is a wave or a particle. Oh, no, it's both. But waves and particles are mutually exclusive. You can't be a wave and a particle. But they are. How are they? Oh, no. Okay. I'm having a conversation with myself, but you get the idea. It is all seriousness. Wave-particle duality is mind-blowing. Particles can't be waves, waves can't be particles, and yet all of reality, it turns out, energy and matter, both are waves and particles. So anytime somebody tells you, the idea that Jesus is both God and man, that's really bizarre. You say, what about the wave-particle duality? And I'm being serious. This is not a smart aleck response. It's a serious one. And to me, this is probably one of the most powerful arguments for defending that theology is not irrational. Now, I don't have a slide for this, but one last definition on your paper, 114, a semiconductor. A semiconductor are substances in which electrons can be made to conduct under certain conditions. And this involves in quantum physics because it is interesting. You actually have a substance where the electrons, in order to escape, they use the analogy of jumping out of a well. This is one I did learn in modern physics. I remember this. This is back in my undergraduate days. And the electron is like in a well, and he has to jump out of the well. And he can't. He doesn't have enough energy to jump out of the well. Well, sometimes he can. And those conditions can be manipulated in such a way that you can give the electron freedom to escape. And so a semiconductor is a substance where electrons can be made to conduct, but only under certain circumstances. There's actually more to that conversation than that, but we're not getting real deep into some of this stuff. We're just trying to touch on it. So we've talked about semiconductors before, so that's a fairly familiar term to you. And then I do want to finish on this, Schrödinger's cat. And what's really cool about this concept of Schrödinger's cat is it's mind-blowing. And it may not be completely accurate. Some people have argued that the whole point Schrödinger was making was that this isn't true. But here's the idea. Imagine you have a box. And in the box, you have a radioactive particle. And that radioactive particle will randomly break down at some point in time. And you have this contraption set up so that when the radioactive particle breaks down, it will trigger, in this case they have a hammer, which will smash the poison and kill the cat. Okay? And so you've got this cat in this box, and you've got this particle in the box, and it's somewhere in the box. And according to this idea of wave particles, it's kind of the whole box. It's kind of in the whole box. It's a wave that's kind of in the whole box. And then you take the box and you split it in half. You put a barrier down the middle of the box to split it into two closed boxes. And the cat is in one side of the box. And the particle is either in one side of the box or in the other side of the box. If the particle is with the cat will die. If the particle is not with the cat will live. Okay? But according to at least some understandings of quantum physics, that particle is neither in the box nor not in the box until there's an observer to observe it. So as long as the boxes are stay closed, not only do you not know if the cat is alive or not, the cat is literally both alive and dead at the same time. And as you take the two boxes, you can take those two boxes and separate them. So they're no longer next to each other. But that particle is still either in one box or the other box, but according to at least some understandings of quantum physics, it is not in either box until an observer observes it. And when the observer observes it, then it's called, I think, like it resolves. And then the particle's in one box or the other box, and the cat will either be dead or alive. But as you take those two boxes and if you separate them, when you open the box, you either have the box when you open that box, the particle will either be in one box or the other, but neither box actually is the particle in until you open the box. But that means the two boxes are somehow communicating with each other, except they're not, of course, they're not connected to each other. And so Schrodinger's cat is considered, according to this understanding, both alive and dead simultaneously until you open the box and discover which it is. But it's not that you learn which it is. When you open it, you actually cause it to be either dead or alive. And at that point, it's either dead or alive, whereas before that, it was neither dead nor alive. I told you guys in Bible class to look up Schrodinger's cat, didn't I? It's really cool. I recommend it. Look up Schrodinger's cat. It's hilarious. It also may not be completely accurate. Some people have argued that this is a thought experiment which is trying to show the ridiculousness of quantum or of certain understandings of quantum. But, you know, it's still amazing. There's actually, when I was in, I guess it's been a long time ago now, there was a cat book called Schrodinger's Kittens. It's a really cool idea. Okay, folks, we finished. You got a summary tomorrow, open book summary tomorrow, and then you'll be done with physics for this year. Turn everything in on Monday. Thank you all for being with me this year in physics. I'm sorry that the year ended the way it did, but thank you all for working with me even in this kind of a situation. And have a good summer. And I'll see a couple of you back in chemistry next fall. And a couple of you, maybe I'll see you at college or around here and there. But anyway, congratulations on finishing physics.